the Science Notes podcast on OAR FM Dunedin, brought to you by the Division of Sciences at the University of Otago. I'm Dave McMorrin. Over the next half hour, I'll be chatting with a graduate science student about their research, their passion for science, and the things that fuel their creativity. Well, hello there, and welcome to Science Notes for another time. My name's Dave McMorrin, and this time our guest is Elouan Hay-Fourmond.
Hello, how's it going?
I'm well. How are you?
Not too bad. Quite happy to be here.
That's the spirit. So Elouan is doing a PhD in chemistry at Otago University. How long have you been doing this?
A bit over a year and a half.
Right.
Inching on 2 years, yeah.
So getting through.
That's the idea.
But not there yet, which is good for me because Elouan does a lot of teaching for me, and I would be ashamed to see him go. Before we get into the nuts and bolts, so you're doing your PhD with Associate Professor Anna Garden, so in physical chemistry. Mm-hmm. How does it that you find yourself doing a PhD with her at Otago?
Well, at first, before I came to uni, I wanted to do genetics, which very different. Yeah, boo, right.
You thought that before you realised what it really was.
Yeah, pretty much. And then...
Sorry, the geneticists out there.
Essentially, I got to have a little bit taste of genetics before uni, and I was like, never mind.
Yeah.
It was like, next thing I like most is chemistry, so I'll go for chemistry. Went through and did an undergrad in chemistry with a minor in genetics, which I regret. And I realized that actually I really liked computer stuff because I got to try a little bit of computer stuff throughout a summer studentship in the department. I realized I really liked that, and well, there's only really one group in the department that does heavily computer stuff. So I went to talk to Anna, who's a great person as well. So I was like, this would be a great group to join. And then I ended up in that group doing some computer chemistry related stuff.
It is kind of a feature of the work that your group does, isn't it? That there is a large amount of coding or AI or all these different aspects of sort of advanced computer type stuff that's being brought to bear on chemistry problems.
Yeah.
And so it's a good place to go if you're interested in that sort of stuff.
Yeah, absolutely. Yeah.
So what then have you spent the last almost 2 years of your life doing in the group?
It is quite the complicated topic to get into. I think the best way to start off is to say that I work on enhancing tools that we use for simulations. So what are those simulations I'm talking about? They're essentially trying to simulate how atoms behave on the nanoscale, so in really, really small areas, right? You can't see what happens there with your eyes or with microscopes, even electron microscopes, because it's too small and it goes too fast. So you're unable to see exactly what happens. So what we want to do is be able to simulate what would be going on down there with some, physical rules and mathematics to see exactly what's happening. And that comes with a lot of challenges, especially in this case, the work I'm doing focuses on clusters. And one of the main challenge is actually being able to figure out what shape a cluster takes. And so clusters are essentially aggregates of a bunch of atoms. So you can have anywhere from, say, 10 to 1,000 atoms. And you can imagine that as soon as you move one atom to a different position, now you could say you've got a different structure, and so you'd have a different cluster.
Right. So what size are we talking about? When you say, well, let's be generous. Let's say 1,000 atom cluster, which is big.
Quite big, yes.
Big in your area. How big is that?
Oh, that is probably a handful of nanometers across.
Right. So a few thousandths of a width for here or something.
Something like that. Something crazy small. There's no chance you can see it with your own eyes.
No, there's no way to use any sort of a microscope type thing. Well,
technically,
you sort of can.
But that comes with its own challenges.
Because the act of seeing it changes the structure and philosophy and
because you shoot electrons at it, so that's going to move it around.
Yeah. So even though, and so why do we care about the clusters?
So the clusters, they're quite fascinating because they have lots of unique properties we don't find on bulk metal. So like, say, a bar of metal, you wouldn't find those properties because they're so small. They have lots of different structures that you can find, and those structures can be used to like make reactions happen faster or emit light, or there's lots of crazy uses you can use for clusters. What we're interested in is catalysis, which is the act of making reactions go faster. And sometimes it only happens for clusters and not the bulk metal, and so we want to know why and what kind of shapes are good so we can make them and we can get lots of catalysis going on.
And why is catalysis good?
Catalysis essentially makes hard-to-obtain chemicals a lot easier to obtain, a lot cheaper, use less electricity, be more eco-friendly, so we could make hydrogen really easily from water or make ammonia without using some really high-temperature, really environmentally bad reactions.
Yeah.
Just makes life easier.
10% of all the energy in the world goes into making ammonia or something stupid?
Crazy like that. So even like a 1% reduction in that would be immense.
Yeah. So clusters then are groups of atoms.
Yes.
Is there a particular type of atom that you're interested in?
So as part of this project, we have looked at 3 different types. The main one we're mostly interested in is gold because it is a notoriously tough case to work with. So
from your point of view?
Yes, because we're working on developing methods, right? So we want our methods to be really robust. We want it to work for the worst case scenario, the hardest scenario we can find. So generally we start off with those to make sure that it will work on anything.
Right.
So we started with gold. And then just to get a better idea of how it works with other elements, we also went with copper and platinum.
So why is gold so hard?
Gold is weird because it has lots of structures that could be the most stable structure, the most likely structure to ever form. And they're all really close to each other, so it's really hard to separate them. So
it's much less discerning in the way that the atoms stick to each other.
Yes, essentially, yeah. It's hard to tell which one is going to be the best, which one's the one you're looking for.
So you're trying to use computers to work out the best way for these atoms to assemble in these different numbers, 100 or 1,000.
Yeah.
Presumably the more atoms you have, the harder it is because the more options you have.
Exactly, yeah.
And according to your notes that you sent me, so your group's been looking at approaches for doing this in a way that doesn't take months and months on a computer. Yeah. And your way that you're exploring is using machine learning.
Yes, yeah.
So tell me about machine learning.
So I think first I need to go a bit more in depth about global optimization.
Absolutely.
So I think the best way I could describe it visually is to imagine that you're in the mountain range, right? Yep. There's lots and lots of mountains around you, and you want to figure out the lowest point in that mountain range, the bottom of the deepest valley. But there's a problem. You can't see what's around you. And the only thing you can do is tell how high up a mountain you are.
Yeah.
And so you can imagine that having to walk around the entire mountain range with only knowing how high you are is going to be pretty tough to find the lowest point. And now imagine that this mountain range is the size of the galaxy. You have a lot of valleys to search through, right? And actually, it's probably a bit of an understatement. It's probably the size of the universe. And you want to find the lowest point. So global optimization is the process of finding that lowest valley, the lowest point in the lowest
without
valley.
Having to walk around the entire space.
Without having to walk through every single meter to make sure that you've checked every spot. And so generally what it does is that it uses some guided guesses to figure out, hey, we're in a low area. This area is relatively lower in the mountain range than everything else. Let's investigate this area more, right? It guides the search so that you don't have to search through everything. The problem is that can still take a while.
Yep.
And if, say, knowing how high up your altitude is takes 10 hours, that's going to be even longer. So some of our work in the group has focused on, trying to figure out how to better guide this search. So you have to go through less valleys. My work focuses on going through each valley faster.
Right.
And that's where machine learning comes in. It can allow you to know your altitude instantly and then move on. So you don't have to sit there 10 hours to know your altitude, right? So you can move from valley to valley a lot quicker.
So your analogy of the mountains then, when we apply it to clusters, is that these low points between the mountains are the happy arrangements of the atoms.
Yeah, essentially.
And you've got lots of different valleys which have slightly different happy-ish arrangements of the atoms, and what you're trying to find is the happiest one.
Yes, exactly.
Because if you then want to experimentally make these to use as a catalyst for making hydrogen or something, that would be the shape that the clusters would take up.
Absolutely. Yeah.
Right.
Yeah. But of course, you can't know it by using imaging techniques, so you have to simulate it.
No, indeed. So then I could controversially ask, so how do you know?
Well, we never know for sure, because to know for sure...
How do you know that you've made the right one, made them the shape that you calculate as being the lowest energy one?
Well, you can't know for sure, first of all, that you have the lowest energy one until you've checked all of them, which we've just established is not possible. So that's already a problem. We can ideally... Well, there's two different ways we can go about it. We can make our simulations. So the step which I've described as evaluating your altitude, figuring out how high up the mountain you are. You can make this step a lot more accurate using better methods. And, the more accurate it is, the longer it's going to take you.
Yeah. And when you say you mean the computer?
Yeah.
And that can mean how long for you for these sorts of things?
It's a cop-out answer, but it depends. With the 13 atom clusters, which I've tested, really small, right? Because we want to go through these tests quickly and not have to wait 2 years to figure out if our options work.
Yeah.
With the 13 atom clusters, generally takes about a day or two to go through 50 different valleys. With 55 atoms, it takes a bit above a week. If we were to have 1,000, it'd probably take above a year.
Yeah.
All right. So it's
hard work for the computer.
Yes.
They're hard calculations to do.
Yeah. And it depends. Is the answer you wanted. Yeah.
So the machine learning then is to try and speed this all up.
Yeah. We want to speed this all up so we don't have to wait the 1 week or the 2 days that I've mentioned. Oh, and actually, I forgot to completely mention the second way we can make sure we have the lowest point that we mentioned, right? We have the happiest structure is by just repeating this whole process many, many, many times to make sure you have the lowest point.
And make sure you get the same answer every time.
Make sure you get the same answer every time. Well, actually, you'll go with the lowest one you find.
Replicates. Nice.
Yeah.
So the machine learning then, it's an AI type thing.
Yeah.
So do you have to teach it how... Because I'm assuming this is all new for this sort of global optimization type stuff. So do you have to teach the AI how to do what it's going to do?
Yeah, absolutely. So since we're working on method development, we want to make a tool that's usable for everyone, for any scenario. So we can't start with a model or an AI that already has information. We can't have it trained right off the bat because the more broadly applicable we make it, the worse it's going to get for every single one of those possibilities, right? So we want to make it really good for this really one task. And so what we do is that we actually teach it how to get good at this task while we're exploring the mountain range, right? So every time we want to figure out how high up the mountain we are, we first of all do it using the expensive way, which is
the really old-fashioned way.
The old-fashioned way, right? Yeah. And then we can take that information, so your original location and the altitude, we take that information and we can feed it into the model so that it can start to learn to correlate location with altitude.
Right.
And so that it can essentially estimate the happiness of the location you're in by where you're in. So it can make predictions without having to go through the old-fashioned process.
And so you do that then for presumably a small cluster where those calculations only take a day or so. Does that then mean that when you then apply the machine learning to the bigger clusters, that's transferable?
That is an interesting question to bring. Some groups in other, universities might want to focus on that because, as you said, it's size of a cluster is really a challenge. The larger they are, the more it's going to cost you. And since we have to do stuff the old-fashioned way, we're still going to have a cost that's really large, which will scale up with the size of that cluster. So ideally, we don't want that.
Yeah.
And other groups have looked at training a model on smaller clusters and then transferring it to a bigger cluster. And that is a valid possibility. It does mean the model won't be as good because it's been trained on a different scenario, right? But for our tool, since we start with a blank slate and we want it to be directly applicable for the structure you're interested in, we only provide information for the model to learn from the exploration of our mountain range for that specific mountain range, right? We don't transfer it to anything else.
Right.
Whatever we learn for that cluster, we use for that cluster.
And in as much as that applies to that particular size cluster, does it also apply to the atoms in the cluster?
Ooh. That starts to get into how we teach the model to recognize a cluster structure.
Right.
So what it does is that it looks at every atom individually and then figures out two things about it. So the first thing it figures out is how far away it is from any other atom. And we call that two-body descriptors, because it just gets the distance from your atom you're interested in with another atom in the cluster. Because
the closer the atom is to the ones around it determines how happy it is. Well, it's one aspect of how happy it
Essentially,
is. Essentially, the energetics of it.
It will feed into it because they interact with each other.
Yeah.
And the other thing it takes into account is three-body descriptors, which means that it looks at the angle between the atom that you're interested in and two other atoms nearby. And so it'll go from one of the other atoms to the atom you're interested in to one of the other atoms and get the angle between the three.
Right.
And it uses that as well. Yeah.
Right. So if you had a plane, a sheet of atoms, then that would be 180 degrees.
Yes.
Because the atom is sort of linear with the two either side of it. Whereas as that angle gets smaller, that means it's kind of coming out into a point or a corner or something.
Kind of. If you have your three atoms in a row, in a line, then yes, you'd get the 180 degrees, right? Because it'd go from one to the middle to the one on the far end, and that's a 180 degree. But if you grab one and you put it at a 90 degree angle, right, it could still be in the same plane.
Oh, true, fair enough.
And you would get a 90 degree angle. Yeah.
But it could also be that it could go forming an edge or a corner or something on a sort of a faceted type.
Yeah. And clusters are generally balls, right? So you're going to get angles of all types. Yeah.
From a point of view of the catalysis, though, this is the end of the calculation is to try and work out the shape. But the catalysis itself it cares about how many edges in these environments of the atoms, doesn't it? So if you have like a completely spherical one where all the atoms are effectively in a plane, that can have different catalytic properties to one that's got lots of angles and points.
Yeah, exactly. And even different corners can interact with different molecules differently. So it's very involved.
And so this is why knowing the structure is important, right?
Yeah,
because
absolutely.
Once you know the structure, then you can start to try and understand why it might catalyze in a certain way.
And if you understand why, then you can replicate it and you can get good catalysts.
And then you can go and do the experiments and make the stuff and save the world.
That's the idea.
So, 2 years in, how are things going?
They're going good, and that we're finally done with the validation step of the work.
Right.
Which means making sure the model works in the first place.
Okay.
Right. So we've tested on small systems only with a small range of different values or different structures that we're looking at. So we only did ever no more than 50 in a row, but obviously there could be hundreds of thousands of them. So we've only tested in small scenarios to make sure it was working properly and it wasn't giving us crazy results. The next step will be to actually go and perform the entire search for that lowest value, for that happiest structure.
Yeah.
Right?
And so you're going to use one of these, the Leonard-Jones, blah, 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 one of these standard ones that everyone knows what the right answer is to test whether your system gets the right answer? Or
Well, actually, no, because Leonard-Jones is actually a quicker method to get the happiness of a structure.
Right.
It's a quicker method, but it's also really, really bad for everything except one scenario.
Right.
So we're using the proper techniques,
Right.
which are a lot more expensive, and then we're making them cheaper with machine learning.
Right.
Leonard-Jones is even cheaper than machine learning, but it's also way worse.
Is that because so many people have used it to study that it's the one that people have come up with the best way for?
It's really quick, so it means it's really good for developing methods, especially if your methods don't depend on the quality of your evaluations of altitude or happiness. If you're only interested in the path you take through the mountain range, you don't care about that too much. So,
right.
Yeah.
Okay, so then you're on to testing using your newly developed technique then.
Yes.
On
gold. Because gold is not as well characterized as Leonard-Jones, but it's still got a whole lot of information out there to compare to, which would be good.
And the idea is, do you have collaborations with people who actually make gold clusters and do chemistry on them, or?
Fortunately not.
No.
No. That would be great. And actually, Anna has got some ideas with regards to that. So that might happen in the future. But
Right.
for now, we're just sticking with developing the method, and then we'll test to see if it works.
Yep.
Yeah.
Yep. And, it might be that the method's useful for someone else down the track
That's
as
the
well.
idea.
It's all just contributing to the knowledge.
I really like doing work that can be used by other people down the line. It makes my work feel a lot more valuable. And so, I'm quite happy doing this.
And, if you compare that to some aspects of chemistry where you make random molecules and you go, look, I made this random molecule, and everyone goes, and why do I care?
What does it do?
Yeah. So you've made it because you can make it. But whereas if you're developing a technique a tool that can be used by other people, then that's a bit more useful.
Yeah. And then it'll have like a flow-on impact. People who use it will hopefully get stuff that's useful for other people, and so on and so forth.
Yeah.
Yeah.
So 2 years in, so you got a bit to go yet.
Yeah.
Thoughts about afterwards?
I have been considering stuff. There's 2 really main ways coming out of a PhD can go. You can either go into industry, work for a big company because, they've got money, they can fund your projects, or you can go into academia where you have a lot of freedom, but you kind of have to find the money yourself.
Yep.
Right. So both of these have their own challenges. They both have their appeals as well. I really like the freedom of being able to work on what you're interested in for academia. So I'm probably partial to that, even with the challenges that come with it. Oh, and there's also the option of always starting your own business, but no, too much effort, too much cost. Not for me. Yeah.
Fair
so
enough.
right now I'd say I'm partial towards academia,
but
I'm not necessarily excited for the issues that come with it either.
Yeah.
Yeah. So I'll probably just delay and do a postdoctorate.
That's the spirit.
Push back the
and then
decision.
do another one.
Yeah.
And then another one. Hide.
We'll see where we go.
Yeah.
Yeah.
Cool. Well, thank you, Elouan, for sharing with us what you've been up to. And all the best for the rest of the research
Thank you.
and whatever comes next. Thanks for listening, everyone. You've been listening to the Science Notes podcast, brought to you by the Division of Sciences at the University of Otago. To listen again or to find other episodes in this series, go to Otago Access Radio's website, oar.org.nz, or to your favourite podcast platform.